So we're going to start, what we're doing today is review. You have technically seen all of this before, but it's been at least 2 years, if not more, because you did a part of this in geometry. So if it looks vaguely familiar, it probably should be, but I'm not expecting you to know it 100%, okay? But it should not be totally foreign to you. We're going to start with a right triangle. What makes a triangle right?
90 degrees.
Okay, how many 90-degree angles can it have? What would happen if it had two? Then it would be a rectangle or something else with two right angles in it. You only can have one right angle to be a right triangle. So we just need to agree on how we're gonna label our right triangles. The right angle is going to be that corner down the bottom left. We put the little square there to indicate that it's right. The sides, the vertical side is always called A. The bottom or base side is always called B, and then the slanted side is called C, which has its own name. Do you remember what that is from geometry? Okay. C is called the hypotenuse, or if you're spelling it, hypotenuse. So the three sides form a relationship. That's true for every right triangle, and this was discovered by the Greek mathematician Pythagoras, and so we name the theorem after him, and this is his Pythagorean theorem. Anybody remember what that is from your SAT classes and stuff? A squared plus B squared equals C squared. All right, that is the Pythagorean theorem. That's the relationship between the three sides of any right triangle will always fall or fit into that formula where C is the longest. C has to be the longest. If your hypotenuse isn't the longest side, then you can't close the triangle or it won't stay right anymore. So it has to be in that form. So how you'll work with this tonight is you'll see some problems that look like this. They'll give you 2 out of the 3 sides and ask you to figure out the third. So maybe they would give you example 1 might be A is 5, C is 13, and then B is up to you to figure out. So you'll get 2 out of the 3. So you'll use the Pythagorean theorem and you'll drop the values into that to figure out the missing third side. So in this case it would be 5 squared plus the unknown B squared equals 13 squared. And then you'll just simplify and solve for B to get B alone. So you'd have 25 plus B squared equals 169. What would I do to both sides? I'm trying to get B alone, B squared alone, so what do I do? Subtract, okay. So when I subtract, I get 144, and then what do I do to both sides? What goes in front of every square root? Okay, so we have a plus or minus the square root of 144, and then I do know that the square root of 144 simplifies to plus or minus 12. So what does it mean to have a plus or a minus for the side of B? So what that means is that if it's the plus side, then your 5, 13, and 12 would be arranged like that, but if it was minus, then the triangle's backwards. And so you still have the 5 and the 13, but the negative 12 would go on the bottom. And so that's fine. Usually we default to positive triangles, but there will be some situations where we'll use some negative triangles. So if it was negative, it would end up looking backwards. The second example with Pythagorean theorem might be something like this, where you have B equals 4, C equals 9, and then A is your unknown value. But again, if it's a Pythagorean triangle, it's a right triangle, you should be able to drop those values right into A squared plus B squared equals C squared. So we'll start with A squared plus B squared is 4 squared, and C squared would be 9. So that's going to give me A squared plus 16 equals 81. And again, you'll use subtraction on both sides, which will get you down to 65. And then the value of A is the plus or minus square root of 65, which doesn't simplify because 65 doesn't have any simple square roots in it. So what would it mean for A to be positive or negative? So if it would either look like let's see, 9 and 4 and positive 65 would look like that. And what do you think it would look like for the negative square root of 65? What do you think? Any suggestions? Any ideas? Okay, reflected over the x-axis. That's exactly right. So it would look like this. You'd still have your 9 and your 4, and then you'd have your negative square root of 65. It would be sort of an upside down triangle. So you're either reflecting over the x-axis or reflecting over the y-axis, depending if you have positive or negative. Okay, that should look vaguely familiar to you. I'm sure it was on the PSAT and in the SAT that you've taken, or ACT. Okay, any questions on Pythagoras or his theorem? Okay, so those are the outside edges. Now we need to talk about the inside. So in addition to having A and B and C, we also have the interior angles. Now we know that one of the angles is 90 degrees. The other angles are labeled with Greek letters. They always use Greek letters when they're talking about an angle. So you'll have angle alpha. Alpha looks like a sideways 8 that's not quite closed all the way. It's where our letter A came from. That sort of morphed into, as our writing changed, kind of like that. It got wider and wider. So can you see how that eventually turned into the letter A? But that's where alpha came from. You don't have to know that, but my writing isn't always the greatest either. So that was alpha. And then the upper corner is beta. And beta, so we have alpha and beta. And beta looks like a capital B, but it's got a tail like that. That's the Greek way to write beta. So if you're interested in sororities or fraternities, you'll learn about the different symbols for the different Greek letters, but that's alpha and beta. And then the right angle is 90 degrees. When you're talking about angles, then we talk about the other part of trig that we need to know, which you maybe remember from geometry, SOHCAHTOA. Okay, SOHCAHTOA. It's a silly little nonsense word, but it helps us remember the order in which the angles are related to the sides. So the sides and the angles are related in a right triangle consistently, no matter the values, as long as it's a right triangle. So what SOHCAHTOA does is it helps us figure out the relationship. So S stands for sine, S-I-N-E. And leave yourself some space, because you'll need some space to write. And then C stands for cosine, and again, leave yourself some space. And then T stands for tangent. These are the big three trig relationships. Now, if you're looking for those buttons on your calculator, the buttons only take 3 letters at a time. And so we usually abbreviate these. And so the sine would drop the E, and the cosine would drop the I-N-E, and the tangent would drop the gent part of it. And so that's what you'll see on your calculator: sine, cosine, and tangent. It's not sin, not sin and cos, but sine and cosine. That's what the S, the C, and the T stand for. Then we need to talk about what the O, H, AH, and OA stand for. So we've covered these, S, C, T. Now we need to talk about the other letters. The H, little h, stands for hypotenuse. All right, that's going to be consistent. The O and the A, anybody remember? Opposite and adjacent. Okay, opposite and adjacent. So look at alpha, okay? And I'll put an angle measure. Come on. There we go. Okay, let's look at that angle alpha. Clearly, the hypotenuse is C. It's always C. But then what's opposite? What does opposite mean, and what does adjacent mean? So adjacent in English means next to or close to. And so what side other than C is closest to the alpha? B. Okay, that's called the adjacent side, which really only leaves A left as the opposite side. So when relationship to alpha, that's opposite. Come on. And that one would be adjacent. Okay, in relationship to alpha. And so what we do is we do this. The formula is sine for alpha, and you do need to specify the angle. After you write sine, you need to put the angle there. You can't just write sine equals, because then I don't know which corner you're talking about. So you have to tell me which corner you're talking about. So sine equals, and then it's O and H. That means we're using the opposite side and we're using the the hypotenuse side. So it would be opposite over hypotenuse. So you can either write the words there, you can write opposite over hypotenuse, or you can write the letters. And so opposite was A and hypotenuse was C. And so if you'd rather just write A over C instead of opposite over hypotenuse, it doesn't matter to me. I'll understand what you mean either way. So you can do it like this, or you can use the words. So sine is opposite over hypotenuse. That's what the O and the H in SO stand for. So for cosine, if we're using alpha, that would be AH, or adjacent over hypotenuse. So you can either use the words adjacent over hypotenuse, so you can either write it like that, or you can actually use the letters for adjacent and hypotenuse, and the letters would be B over C. And then finally for tangent, tangent for alpha, that would be TOA, or O and A, so that would be opposite over adjacent, so you could use the words, or you can use the letters, and the letters would be A over B. So it doesn't matter to me how you do it. Those are the big three. So TOA stand for sine, cosine, tangent. Again, this should sort of be familiar because you did it right triangle, trig, and geometry, but I know it's been a long time. If you change to beta, then the opposite and the adjacent are different because beta has a different adjacent side than alpha does. So if you're switching to beta, if you do sine beta, then its opposite is B and the hypotenuse is still C. So that's why I usually don't use the letters. I just use the words. I would just use opposite over hypotenuse if you switch. Any questions on that so far? Okay, then you have three more. Each of those has a pair or a reciprocal that goes with it. Let's work backwards. What goes with tangent is cotangent. But again, you can't fit cotangent on a button, so we abbreviate that to just COT. But again, if you notice, there is no COT button on your calculator. That's something that you have to know. Your calculator doesn't do it on its own. What is cotangent? Cotangent is the reciprocal of tangent. I'm going to go back to words a minute here, if you don't mind. I'm going to change tangent back to TOA. If tangent is TOA, which is opposite over adjacent, then cotangent is adjacent over opposite. It is the reciprocal. You flip. Okay, the numerator and the denominator just flip. That is the relationship between tangent and cotangent. If you work backwards, cosine also has a corresponding reciprocal. Its corresponding one is secant, but we abbreviate that as just SEC. And so the secant, based on the alpha angle, is the reciprocal of cosine. So again, if I change the words of cosine back, to adjacent over hypotenuse, then this would be hypotenuse over adjacent. So once you know cosine, you can just flip them, and then you have secant automatically. And then the last one is the longest. It is cosecant. All right. Does anybody see a problem with abbreviating that? What do you see, Veronica? If you just abbreviate it the same way you've done all the rest of them, if you just take only the first three letters, now you have COS again, which is the same thing that you already had for cosine. So we can't just do that. This is the only one that needs a unique abbreviation. So to help us know that it's cosecant and not cosine, we say CSC. That is cosecant. And for the relationship of alpha for there, you look at what sine was. All right, well, sine was opposite over hypotenuse. This was OPP over HY, hypotenuse, or opposite over hypotenuse. And so for cosecant, we switch them around. You really only have to memorize the first three and then memorize which ones go together. Here's some memory tricks. Cotangent and tangent, those are pretty easy to know. Those two go together, but what about the other two? A lot of times I see people getting mixed up, and they think that cosecant and cosine go together because they both start with the prefix co. So they think that these two go together because they both have CO at the beginning, cosine and cosecant. Oh, they must be paired because they're both CO. You just got to keep straight that you can't, two things with cos can't pair together. And so cosine would not pair with cosecant. Cosine pairs with secant. Another way I remember it is I switch the outer two letters. So COS, and then it's S and C switch, and that helps me. I don't know, however you want to pair those together. All right, so I hope it'll make a lot more sense once we get some numbers in there. So those are the basics. Once we get some numbers in there, I think it'll start coming together. So let's try it with some actuals. So our first example will be the following. All right, A is 3, B is 4, C is 5. State the 6 trig values. So you'll start with the first big 3. So you want to state the first 6 trig values for alpha. Okay, state the 6 trig values for alpha. It helps me to draw a picture. If you can do it without drawing a picture, if you can do it in your head, but it helps me to draw a picture. So I know all the sides are positive, so I'm going to create a picture, and I put alpha down in the corner that I need alpha to be. And then I'll put the numbers on there, so I know A is 3, and the bottom number is 4, and the hypotenuse is 5. So I've got everything on there that I need. So I do my big 3 first, my first 3 trig values. I'll do sine, cosine, and tangent first. So I usually write it like this. I do sine, and I write alpha, so I remember that I'm using the alpha corner. Cosine, alpha, tangent, alpha. And until you have these memorized, it might be helpful for you to write the different SOHCAHTOA things down. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. This is the SOHCAHTOA, S-O-H-C-A-H, tan O-A, T-O-A, until you have it memorized. Once you have it memorized, you probably can skip that step. But in relationship to alpha, what number is on the opposite side? 3. And what number is on the hypotenuse side? 5. That's it. 3 over 5, you're done. And then adjacent to alpha, the adjacent, the closest one is 4. The hypotenuse is 5. And then for tangent, the opposite, farthest away, is 3 over the adjacent is 4. And that's all it takes. It's just rearranging those numbers into groups of 2 and writing them as fractions. This is why I've been hitting fractions so hard all semester. Fractions, fractions, fractions. Because in trig, it's only fractions. Okay, fractions are the only things that exist. Once you have the first big 3, then you can do the second 3. And so if I work my way backwards, I know tangent is cotangent. And so for alpha, if tangent was 3 over 4, then cotangent is 4 over 3. You just flip it upside down. For cosine, COS, I switch to SEC. Those two go together. If it was 4 over 5, now it's 5 over 4. And then alpha for cosecant, CSC. If it was 3 over 5 for sine, it must be 5 over 3 for cosecant. All right, let's try a different set of numbers. So our next example, our next SOHCAHTOA example, let's work with B to be 3, C to be 10, and we're going to work on the beta angle. So B is 3, C is 10, and we're going to work on the beta angle. We're going to find all 6, same as before. So we'll set it up. B is 3, so that's going to go on the bottom. C is 10, so that's the hypotenuse. Beta is the upper corner, so I'll get that labeled up there. What is missing? A. How do I find A? Because I can't do any of the other stuff until I have A. Okay, I got to go back to Pythagorean theorem. So I'm going to have to do a little timeout from my SOHCAHTOA trig, and I need to go back to Pythagoras. So I'll go back to Pythagorean, which says a squared and b squared equals c squared, because the a part is the part that I'm missing. Okay, that variable a, which goes on that left-hand side. So I don't know a squared. I do know b squared is 3 squared, and then c squared is 10. So I'm looking at a squared plus 9 equals 100. And when I square root, or when I subtract, I get 91. And so a is the square root of 91, plus or minus. This is a positive triangle, so I'm only going to use the positive part of it. So now I know that a is equal to the square root of 91. Now that I have the 3 parts, the 3 pieces of the sides, then I can do my big 3 of my trig values. So now I'm ready to do sine based on beta, cosine based on beta, and see if I can fit it on there, tangent based on beta. Remember, beta is the upper one. Okay, I'll take a volunteer if somebody wants to try it. What is the sine relationship to beta? Okay, it's opposite, which is the farthest one away, which is 3, over the hypotenuse, which is 3 over 10. Now, if that was reducible, you should reduce it. 3 over 10 isn't, but if it was, you need to. So cosine is the adjacent, or the closer one, so that means rad 91 over 10. And then tangent is TOA, so that would be the opposite side, which is 3 over the adjacent side, which is 91. And you'll be glad to know that in square roots, you don't have to rationalize. It's okay to leave a square root in the denominator, so you're good to go with that. Once you have the first big 3, then you just can quickly convert to the second 3 by pairing it up. So tangent pairs to cotangent, and you flip them, so the rad 91's on top and the 3's on the bottom. For cosine, COS changes to SEC, beta with a tail, and that becomes 10 over rad 91. And then sine is cosecant, or CSC, of the beta, that would be 10 over 3. All right, how are we doing? Questions so far on any of that?
Why don't you put a plus or minus in front of the
Okay, I didn't write all of the instructions that you would have seen in the, it was good, really good question. We would have had something here that would have said that A is greater than 0. And so that means we're only working with positive values. That would have been in the instructions of the problem, and I just neglected to write all that down. Okay, good. Our last example in this section. All right. Cosine theta 5/11. Find all 6. All right, here's something new. What's new? I have a different Greek letter. Okay, that's the Greek letter theta. So let me spell those for you. So we've got alpha, we have beta, now we have theta, Theta. Okay, sometimes people misunderstand what I say and they think I'm saying, I can't write it. Come on. There we go. People think I'm saying this. F-E-T-A. Okay, that's a cheese. That's feta cheese. It's not feta. It's theta with a T-H. So, and theta is written as an open circle with a line horizontally through it. There's a different Greek letter that's open circle with the line down that way. That's a different Greek letter. Okay, that's phi. But this is theta. All right, so that's what I'm talking about. Now, where does theta go on the triangle? Theta is actually my favorite because it doesn't matter. You can put theta wherever you want as long as you don't put it in the bottom angle. So it does not matter if you put theta up in the upper or in the lower. You're going to get the same answers either way. Okay, so it does not matter. So I'm going to go ahead and just put it up here just for arbitrary sake. Okay. Now, what I know, and I've got to find all 6. So let's just kind of set ourselves up here. We want to find sine of the theta corner. We want to find cosine of the theta corner. And we want to find tangent. So those are the big 3. And then we'll also are going to need to do cotangent, secant, and cosecant. So it's sort of like a puzzle. Okay, it's finding the clues and figuring it out. So we were given at the outset 5 and 11 as the answer. So we've got one of them. We were given one of them. What comes with that? When you know cosine of theta turns out to be 5 over 11, what automatically can you deduce from that? Okay, and the SEC would be 11 over 5. Okay, great. So 2 down, we only have 4 to go. What we now need to do next is get the 5 and the 11 on the right places of the triangle. So cosine is SOHCA-TOA. It comes from the A and the H. And so if I look at that 5/11ths, that means that the 5 has to be on the adjacent side, and the H has to be on the hypotenuse side. So that helps me place the 5 and the 11 on the right place and the right positions. So if I want 5 to be adjacent, I need to put 5 right here so that it's adjacent to the theta corner. And 11 is the hypotenuse, so I'm going to put 11 on that corner, which really just leaves this bottom value for me to figure out, which again goes back to the Pythagorean theorem so that I can figure out what that value is. And so I'll use Pythagorean. So a squared plus b squared equals c squared. So I'm going to have 5 squared plus, I don't know yet, and then 11 squared. So that's 25 plus b squared equals 121. And when you subtract 121 and then 25, what do you end up with? 96. So b squared is 96, which means b has to be the plus or the minus square root of 96. We're only going to use the positive side, but we do need to break down 96 because there's numbers that go into 96. And in fact, it could be 16 and 6. All right, 96 breaks down into 16 and 6, which means this question mark for me, I now know to be the value 4 rad 6. That was square root 16, square root 6, which allows me to finish the problem. Now that I know that 4 rad 6 is on the bottom, that is the side farthest away from the theta, and so that's my opposite side. So 4 rad 6 and 11 is the relationship for sine. That's so, S over opposite over hypotenuse, which means cosecant would be 11 over 4 rad 6. And then tangent is the only one left. That's TOA. So that would be the opposite, which is 4 rad 6, over the adjacent, which is 5. And so then 5 over 4 rad 6. All right, last thing. Now this is a mixture of algebra and trig. Solve for x. Okay, that's back to algebra. Get x by itself. Solve for x. So I'm going to give you a picture. Picture is going to look like this. Okay, x is sitting in the hypotenuse position. 15 is sitting in the vertical position. And the alpha angle is 34 degrees. Okay, that's the picture I just drew. All right, so 34 is in the alpha position. What's 15 in? What position is 15 in? That is in the opposite position. What about x? Hypotenuse. So this is alpha. What trig uses alpha and opposite and hypotenuse? Sine. Okay, opposite and hypotenuse with alpha is sine, because that's SOH. S-O-H. So if I have opposite and hypotenuse, I want to do S-O-H, because I have opposite and hypotenuse. So I'm going to use the formula. Sine alpha is opposite over hypotenuse. Now just drop all the numbers in. In the alpha position, drop 34. In the opposite position, drop 15. In the hypotenuse, drop x. So we're going to have sine 34. In the opposite position, I put 15. And then I have x down there. And now I want to solve for x. Any ideas? Yeah, what's our clue for cross multiplying, right? What do we put under the sine 34? Drop a 1. And then we get to cross multiply. So x cross multiplies to sine 34 degrees. And 15 cross multiplies to 1. So x times sine 34 equals 15. And how do I get x by itself? Divide. So x is 15 divided by sine 34. All right, now your calculators were set to the right mode. Go ahead and grab your calculator at this point. Type in 15 divided by sine 34, and you're already in degree mode, and so you should be able to get an answer. And this is the only time you can use decimals in trig, is when you're solving for x. Okay, so try typing that in, 15 times sine 34. Does anybody have it? 26.8, always go to 3 decimals. What comes after the 4? A 3, so we're good to leave it there. Okay, 26.824, awesome. Okay, one more and we're done. All right, last one is also solve for x. All right, this time the picture looks like this. Okay, the right angle down here. X here, 27 and 39. Okay, so 39 is in the alpha position again. What's 27 in? Hypotenuse. What about x? Adjacent. All right, what trig formula, uses alpha and adjacent and hypotenuse?
Cosine.
Cosine. So this time it's CAH because I was using adjacent hypotenuse. So the cosine formula is cosine of alpha is adjacent over hypotenuse. So you'll drop the values in. So the cosine of 39 degrees is adjacent, which is x, and hypotenuse, which is 27. This is another opportunity for you to cross multiply. So cross multiplying 1 to x is x by itself. And then 27 cross multiplies to 39 degrees cosine. You just type that right in, and you'll have your answer. Homework help starts tomorrow. So start the semester off right. Homework help, come on in. Tomorrow morning I'll be here if you're having trouble with any of the SOHCAHTOA stuff.